Today we are going to learn about mastering policy gradient methods in deep RL. We will dive into the fundamentals of policy gradient methods, how to implement them effectively, and how to optimize decision-making in complex environments. Welcome to our session on mastering policy gradient methods in deep reinforcement learning. Policy gradient methods are a class of algorithms in reinforcement learning that focus on directly optimizing the policy, which is the strategy that an agent follows to make decisions. Unlike value-based methods, which aim to estimate the value of actions or states, policy gradient methods aim to find the best policy parameters that maximize the expected reward. This approach is particularly useful in complex environments where value estimation can be challenging. Throughout this video, we will explore the advantages of policy gradient methods, understand the underlying mathematics, and learn how to implement and tune these algorithms for optimal performance. In reinforcement learning, methods can broadly be categorized into value-based and policy-based approaches. Policy gradient methods offer several advantages over traditional value-based methods. Firstly, they directly optimize the policy, which allows for more efficient learning in environments with continuous or high-dimensional action spaces. This direct optimization helps in reducing the approximation bias that can occur in value-based methods. Moreover, policy gradient methods are more flexible in representing policies, allowing for complex decision-making strategies that can adapt to various tasks. These advantages make policy gradient methods a powerful tool for tackling problems where value-based methods struggle, particularly in real-world applications with complex dynamics.
The Policy Gradient Theorem is a cornerstone of policy gradient methods. It provides the mathematical foundation for optimizing policies through gradient descent. The theorem states that the gradient of the expected reward with respect to the policy parameters can be estimated using the expected gradient of the log probability of the actions, weighted by the rewards. This allows us to perform gradient descent to improve the policy iteratively. Understanding this theorem is crucial, as it underpins the development of various policy gradient algorithms. By leveraging this theorem, we can design algorithms that effectively optimize policies to achieve better performance in reinforcement learning tasks. The reinforce algorithm is one of the simplest policy gradient methods and serves as a great starting point for understanding policy gradient implementation. It involves sampling episodes from the environment, calculating the cumulative reward for each episode, and updating the policy parameters using the policy gradient theorem. The update is performed by adjusting the parameters in the direction that increases the expected reward. However, implementing reinforce can be challenging due to high variance in the policy gradient estimates. Despite this, mastering reinforce is essential, as it lays the groundwork for understanding more advanced policy gradient methods.
One of the significant challenges in policy gradient methods is the high variance in the gradient estimates, which can lead to unstable learning. Variance reduction techniques are crucial to mitigate this issue and improve learning stability. A common method is baseline subtraction, where a baseline is subtracted from the reward to reduce variance without introducing bias. Another technique is using advantage functions, which measure how much better an action is compared to the average action. Generalized advantage estimation further refines this by providing a more stable estimate of the advantage. These techniques are vital for enhancing the performance and stability of policy gradient algorithms.
In modern reinforcement learning, policies are often parameterized using neural networks due to their ability to represent complex functions. This parameterization allows for flexible policy representation, enabling the agent to learn sophisticated strategies. When designing neural networks for policy representation, considerations include the network architecture, activation functions, and optimization techniques. Training these networks poses challenges such as handling exploration-exploitation trade-offs and managing overfitting. Despite these challenges, neural network-based policies offer scalability and efficiency, making them a popular choice in deep reinforcement learning for solving complex problems. While policy gradient methods are powerful, they come with challenges that need to be addressed for effective implementation. One major challenge is balancing exploration and exploitation, where the agent must explore new actions while exploiting known ones to maximize rewards. Sparse rewards, where rewards are infrequent, can also hinder learning. To overcome these, techniques such as reward shaping and intrinsic motivation can be used. Avoiding local optimize is another challenge, often tackled with techniques like simulated annealing or entropy regularization. Additionally, policy gradient methods can be sample inefficient and computationally complex, requiring efficient use of computational resources and algorithmic optimizations to ensure practical applicability. Policy gradient methods have a wide range of applications in real-world scenarios, showcasing their versatility and effectiveness. In robotics and autonomous systems, these methods enable robots to learn complex tasks, such as navigation and manipulation, by optimizing their decision-making policies. In game playing, policy gradient methods have achieved remarkable success, particularly in strategic games like Go and chess. They are also used in natural language processing for tasks such as dialogue management and text generation. In the finance industry, policy gradient methods optimize trading algorithms by adapting to market conditions. In healthcare, These methods are applied to develop diagnostic tools and personalized treatment plans. These applications demonstrate the powerful impact of policy gradient methods across various domains.
In this video, we have explored the fundamentals of policy gradient methods in deep reinforcement learning. We discuss their advantages over value-based methods, the importance of the policy gradient theorem, and how to implement and tune these algorithms effectively. We also highlighted the role of variance reduction techniques in improving learning stability and the significance of parameterizing policies with neural networks. Addressing common challenges and exploring real-world applications showcase the broad impact of policy gradient methods. We hope this session has provided valuable insights and equipped you with the skills to leverage policy gradient methods in your reinforcement learning projects. Thank you for joining us.